Good morning, everyone. Today we're pleased to have Tong from University of Chicago talk to us about electroweak baryogenesis.
Thanks for the introduction and invitation. I am a grad student from University of Chicago. And today I will be talking about electroweak baryogenesis with CP violation from the dark sector. So before I get into the specific model, I want to give an overview of baryogenesis. We know that there are more baryons and antibaryons in the universe, which is measured to be this number. So there are two possible scenarios leading to this fact. The first one would be the universe start with a non-zero baryon number. However, there are two issues with this scenario. Is first that we need an extremely fine-tuned initial baryon number to explain the observed value, which is very small. And second, in an inflationary universe, inflation would exponentially dilute any amount of initial baryon number. A more favorable scenario is that the universe starts from an initial state with equal number of baryon and antibaryon and generate the baryon asymmetry through dynamical process. This scenario is called baryogenesis. And the necessary conditions for baryogenesis are known to be the Saffras conditions, which is that we have to introduce baryon number violation process. We have to break charge and charge parity symmetry. And the process has to take place in an out of equilibrium environment. So in this talk, I will focus on electroweak baryogenesis, which is a mechanism that generates baryon asymmetry and electroweak phase transition, which is the phase transition during which the Higgs boson gets defined. So I want to give an overview of how the free Saffras conditions are satisfied in electroweak baryogenesis. So for baryon number violation, this can be realized through the Weak's theorem, which is available in the standard model. So to understand what this is, we first introduce the consignment number, which quantifies the topological charge of a gauge field configuration and is related to the baryon and lepton number as the following. So if the consignment number changed by 1 unit, the baryon and lepton number would change by 3 units, respectively. And the energy of the gauge field configuration as a function of the consignment number is of this shape. So we can see that the minimum of this energy of the energy appears at the consignment number being integer. So around each minimum, the fluctuation around this minimum can be described by perturbation theory. However, the transitions between two neighboring minima is a non-perturbative effect, and it could proceed in 2 ways. One way is just hop over the barrier by thermal effects, and this is called the sphalerem. And the other possibility is to tunnel through the barrier, and this is called the instantron. So for baryogenesis, we are interested in the sphalerem process, and the rate of the sphalerem is related to the energy barrier, which is proportional to the width of the Higgs, as U2 is spontaneously broken. So from this, we can see that the sphalerem rate is actually unsuppressed if V is equal to 0. And this provides the source for baryon number violation in electroweak baryogenesis. So in that case, the gauge field for us would be the SU2 gauge field. So this is the baryon number violation. We have the available in the standard model. So now the second condition is the CP violation. I add the electroweak light baryogenesis. By this, I mean there are a bunch of baryogenesis mechanisms in which they don't directly use electroweak phase transition, but they utilize some kind of first order phase transition. In that case, the scalar field is not the Higgs, but it's a first order phase transition. I mean, in general, for this kind of baryogenesis, a typical CP violation source would be the complex mass of a fermion. So I show here the bubble wall profile. So here is the y-axis would be the value of the Higgs, which is varying across the bubble wall. So by coupling to the Higgs field, the top quark can get a mass, of course, but in the standard model alone, it would be a complex mass, but with a very small complex phase, as I will mention later. So usually we consider in the extensions of the standard model, the top quark can get a complex mass by Yukawa coupling, which varies along the bubble wall with the Higgs wave, which takes this form. So we have both the varying magnitude and the phase, which are both critical for CP violation. So with this mass turn, because we have gamma 5 here, the left-handed and the right-handed fermions interact differently with the bubble wall. And also, the left-handed particle interact differently from its CP conjugate, which I call L bar. So as a result, the left-handed particle is reflected at a different rate from its CP conjugate. And this, so in this picture, we have equal number of L and L bar coming in, and they scatter at different rate. And the result would be that there's a net number of left-handed fermion generated in front of the bubble wall. So this would create a chemical potential that would drive the weak spherogram to generate more baryons than antibaryons. So as I just mentioned, there is CP violation in the standard model, which is, well, what's relevant for the electric baryogenesis would be the one in the quark sector, which is the CKM matrix. But people have found that so the CP violation in the quark sector could be quantified by this Roscoe invariant. And if we normalize this by the electroweak scale, we found this to be 10 to minus 20, which is very small, even much smaller than the observed baryon asymmetry. However, people have considered this to be the only source of CP violation for electroweak baryogenesis back in 1993. However, this paper was later refuted by these two papers for not correctly accounting the plasma effect. So in conclusion, people usually consider the CKM matrix alone is not sufficient to provide CP violation for electroweak baryogenesis. And the last Sakura condition is out of thermal equilibrium. So again, in baryogenesis that generally depends on first order phase transition, the role of the first order phase transition is to provide an out of equilibrium environment. So what is first order phase transition? So this is a plot, a schematic of that. So we have phi equal to 0 is the false vacuum, and phi not equal to 0 is the true vacuum. So we have these bubbles of the true vacuum forming out of the false vacuum, and they expand, eventually turn the whole universe into the true vacuum. This is how first order phase transition happens in the universe. And this plot is a summary of how these three ingredients come together to generate baryon asymmetry. So we have this bubble wall forming and it's moving, and sorry, and we have particles of different chirality and particle and antiparticle coming in at equal amounts, and they scatter with the bubble wall. And due to CP violation, the left-handed particle scatter differently from its CP conjugate, and that could generate a net amount of left-handed particle in front of the bubble wall. And as we said in the spherogram slide, the spherogram is unsuppressed in the symmetric phase where the wave is 0. So outside the bubble wall, the spherogram is active and it could turn the CP violation into baryon asymmetry. And this baryon number will eventually diffuse into the true vacuum or the broken phase in which the spherogram is suppressed. So wherever we generate outside here, once it's diffused into the broken phase, is conserved because there's no baryon number violation in the broken phase. Okay, so now again, we want to check whether the standard model would give us a first order phase transition because we know we are now in the vacuum where the Higgs wave is non-zero. If we assume SU2 is restored in the early universe, there must be a phase transition somewhere in the evolution of the universe. We just want to know if this is first order in the standard model. So to understand this, we have to look at the finite temperature effective potential for the Higgs field, which at one loop level takes this form. So we have the chi level potential, and this V1 is the one loop correction at 0 temperature, which is also called the Coleman-Weinberg potential. And we have this one loop correction at finite temperature. And this B and F stands for boson and fermions. So we have the sum over all the particle species that couple to the Higgs field to account for the thermal correction. And to get some analytic insight, it's useful to expand the thermal functions, JB and JF, to the leading order terms in terms of this M over T. So we are taking the high temperature limit where this is much smaller than 1. So we have this leading order contribution to JB and JF. So, and this is V effective at leading order at high temperature. So we have the quadratic term, the cubic term, and the quartic term. So now we can analyze the shape of this potential at different temperature. So at very high temperature, where this quadratic term dominates, the V effective would be just like the quadratic potential of H. So this is, in this case, we have only one global minimum at H equal to 0, where SU2 is restored. And as temperature drops, this cubic term becomes important, and it will introduce this barrier between, so it will introduce another minimum at H not equal to 0, with a barrier separating it from H equal to 0. And at temperature, at the critical temperature Tc, these two minimum become degenerate. So around this temperature, a first order phase transition could happen. And as temperature continues to drop, the minimum at H equal to 0 vanish, and we are left with only one minimum at H not equal to 0. And this is our vacuum today. So, and also I want to mention that at Tc, the two minimum become degenerate, but it's not sufficient for the bubbles to form, because for a bubble to nucleate, it has to conquer the surface tension around the bubble. So if the temperature, if the energy difference is 0, it's not sufficient to conquer this surface tension, so it would not form. So bubbles actually nucleate at a temperature lower than Tc, where we have energy difference between the two vacuum. So then the bubble nucleation could become significant. And this is the nucleation temperature that you will see in baryogenesis literature. So in addition to first order phase transition, remember that we, in this slide, we said that we want the baryon number generated outside the bubble wall to diffuse into the broken phase, and it's preserved in the broken phase. Otherwise, the spectrum could generate baryon number, but it could also wash out baryon number, and we don't want the washout to wash out the baryon asymmetry. So to satisfy this requirement, we want the spectrum rate in the broken phase to be very suppressed. And remember that the spectrum rate is proportional to exponential E spectrum over T. And E spectrum is proportional to the width of the Higgs. So this indicates that we want En over Tn, by N I mean nucleation. So the Higgs width in the broken phase and nucleation temperature over the nucleation temperature is much larger than 1. And this is usually referred to as the strong first order phase transition in baryogenesis literature. So now we want to check if the, okay, something I forgot to mention is that our previous question of whether the standard model would provide us a first order phase transition, the answer is yes, based on a perturbation study, because we have a non-zero qubit turn in the standard model. So yes, it would provide us a first order phase transition. However, if we estimate VC over TC, where C means critical temperature, this is just because critical temperature is easier to evaluate. So people usually use VC over TC as an analytic quantify of the strength of the phase transition. So this is estimated to be E over this in the standard model, and it's roughly of this order, and this is much smaller than 1. Even if the standard model could provide a first order phase transition, is not strong enough for baryogenesis for this reason. And in addition, this is perturbative analysis. Non-perturbative lattice calculation has shown that for a first order phase transition to happen in the standard model, the Higgs mass has to be lighter than ATG, which we know is not true. So that already ruled out the standard model as the source of a first order electroweak phase transition. So what should we do if we want a first order electroweak phase transition? Well, the simplest remedy is to introduce a standard model singlet scalar field, which couples to the Higgs by this quadratic coupling, and also has this general quadratic and so how this would solve the problem for us is we can first calculate the mass of the scalar field, which is mu square plus this term coming from the is coupling with the Higgs. And we can substitute this into the high temperature thermal function in the effective potential, and then we get a turn like this. So we can see that this turn adds to the qubit turn of the Higgs at chi level, because it's proportional to lambda SH, and lambda SH is a chi level coefficient. So in this way, we can enhance the standard model qubit turn, and we know VC over TC is proportional to E. So this would enhance the phase transition strength in the standard model, if there is one. Okay, so a summary of Sakura's conditions in the electroweak baryogenesis is standard model provides us an efficient baryon number violation process, which is the big spectrum in the electroweak symmetry unbroken phase. So that is good. A lot of baryogenesis rely on weak spectrum. And regarding CP violation and first order phase transition, there is CP violation and phase transition in the standard model, but they are not strong enough to produce the observed amount of baryon asymmetry. So before I move on, any questions on this part? Yes.
Yeah, thanks. Maybe just kind of looking at this from the experimental perspective. So you mentioned essentially that if the trilinear term for the h cubed was larger, right, than the standard model from, say, this model you introduced, that at some point you can explain the level of baryogenesis. But do you have some idea how much bigger it has to be? Like, is that within the realms of what we
The cubic term?
constrained yet? Yeah, the cubic term, I mean.
Yeah, so it's it has to be large enough so that this term, well, I guess in extension of standard model, this could change. As long as this is of order 1 that we consider is dominant. So
Okay, so you're saying the DC over DC should be roughly order 1, which would in the E scale, I guess it's high here, right? So you need
the energy scale for the phase transition or for the singlet?
Yeah, I'm just trying to, because okay, in the standard model, lambda is what, like 0.13, something like this. So how big, roughly speaking, does lambda have to be to pivot in this picture? To explain baryogenesis. See what I mean? Maybe I didn't phrase it right.
Yeah, sorry. So you said E scale, does it mean DC or N?
Yeah, I'm just like, how much of an enhancement do you need kind of in the term?
Yeah, so usually in this scenario, people usually would consider lambda SH to be order 1 for sufficient VC over TC.
Okay.
Yes. Yeah, but this is model dependent.
Sure.
Yeah, so actually, as I will show later, we have a much lower lambda SH, which can also satisfy the requirement. Yeah, so and it's also for sure constrained by experiments as well. So all
Of
that.
course, but okay, so if I look at the last formula here, right, if lambda SH is order 1, then you're adding effectively h cubed term at the level of lambda SI, right, the same order. So
Yeah, right.
it's, I don't know, something like 1 over 0.13 level bigger enhancement in that term, right? In the sense that experimentally, we basically measure the h cubed, right, whatever the contributions are.
Yeah.
So there it's like level 5-ish times this thing, right?
Yeah, that's right. There are no questions. I will move on to the model. In this model, we are doing a very typical type of electroweak baryogenesis, meaning we are using the same source of baryon number violation as in most of the electroweak baryogenesis, which is the Weak's phaleron. And for out of thermal equilibrium, we are also using the same source. It's a strong first order electroweak phase transition. So what's new here is CP violation. So as I said, top quark could provide CP violation. In our case, we have the dark fermion playing the role of the top quark. So one challenge of this is that CP violation is introduced in the dark sector, but baryogenesis should be in the standard model sector. So we have to construct some kind of portal to transfer the CP asymmetry to the standard model sector. And this idea was first proposed by my advisor, Marcela Carina, and collaborators. And later on, we have a paper that calculated the phase transition history carefully. So why do we want to break CP symmetry in the dark sector? The reason is the electron EDM measurements. So any kind of CP violation that couples to the standard model fermions is constrained by the measurement of electron EDM, which is very tight. But if we introduce CP violation, the dark sector, then this typical diagram generates EDM. In this block, we would have 2 more loops. So here, this R and A, they are the scalar field that the singlest scalar couples to the Higgs, and this chi is a dark fermion. And this Z prime, as I will introduce later, is a new gauge boson. So by this diagram, this becomes a for loop diagram for the electron EDM. So this could be easily suppressed below the experimental constraint. So now let's get to the details of the model. As a starting point, we promote the lepton number to a gauge symmetry, U1L, with a new gauge boson Z prime. And because this U1L is anomalous with respect to the standard model gauge symmetry, so additional fermions have to be introduced for anomaly cancellation in the UV. In addition, we also introduce a complex scalar field phi charged under U1, which gets a wave at above TeV scale, so way above electroweak scale. And this spontaneously break U1L and give all the new fermions heavy mass at the TeV scale, except for one lightest one, which we call chi. And so we can do that by assigning a very small Yukawa coupling of chi to phi. So it gets a wave at about 100 GeV, which is the scale of the electroweak phase transition. And also for the gauge boson Z prime, we also want it to be active around the electroweak scale. And so to do that, we have to assign a very small gauge coupling G prime so that it gets a mass at 100 GeV scale. So at the electroweak scale, we can integrate out all the heavy particles at TeV scale so that only chi and C prime remain active at the electroweak phase transition. And the effective gauge interactions are this. So we have the dark fermion, chi, and the standard model leptons coupled to Z prime. So now how do we break CP symmetry? We have to introduce another new particle that it's a complex scalar and it's singlet under the standard model. So it's not only for CP violation, which it does by coupling to the dark fermion chi by a complex Yukawa coupling. And there's another reason for introducing this dark scalar is to induce a strong first order electroweak phase transition following the mechanism I introduced earlier. So it couples to the standard model Higgs by this quadratic coupling. And for CP violation, we have to introduce this additional term, which has a complex coefficient. So then we have two complex coefficients here, which guarantee that the phase of the mass turn of chi cannot be removed by redefinition of S. So for baryogenesis calculation, we usually calculate this CP violation source, which is proportional to the mass turn, and this is the phase of the mass turn derivative and double derivative. So this indicates that it's not only we not only have to have a non-zero phase of the mass, but it also has to take a non-trivial profile for a non-zero CP violation source. So this is what we found in numerical calculation. We indeed have a varying phase of the mass turn across the bubble wall, and so that we have non-zero CP violation source around the bubble wall.
This S does not have any charge under your U1L.
The S?
Here.
Yes, that's right. Yeah, it only charge under U1L. So then the question is, how do we transfer the CP asymmetry in the dark sector to the standard model sector? And the answer is through the Z prime portal. which talks to both the chi and the standard model leptons. So near the bubble wall, we break CP symmetry, and we generate this a non-zero number of L, chi L minus chi L bar. And we also generate an equal amount of chi R minus chi R bar. And the crucial thing to observe here is that the left-handed chi L and chi R carry different amount of charge. And this is assigned by anomaly cancellation in the UV. Because of this, we have a non-zero charge density of non-zero lepton number charge density near the bubble wall due to this term. So this charge density would generate a Coulomb potential of Z prime. And because Z prime couples to the standard model leptons, this Coulomb potential could provide a chemical potential for the standard model leptons. So then that would change the equilibrium number of the standard model lepton. And that would drive the spherogram to generate more lepton than anti-lepton. And remember that the weak spherogram could change baryon number and lepton number respectively, but would preserve B minus L. So that would effectively convert the lepton number to baryon number. So eventually, we get baryon number out of this non-zero lepton number. So maybe I should pause here for questions. Then I will focus on the phase transition history of this model, which is crucial. So again, we write down the scalar potential, the effective potential at one loop level at finite temperature. So we start with the shear level potential, which we can expand in terms of all the real fields. In this case, we have three fields, Higgs, and the real and imaginary part of the complex singlet. And we have to introduce the Coulomb-Weinberg potential. And this is the counter term that is to counteract the loop correction, the Coulomb-Weinberg correction, and fix the zero temperature at the observed value. At finite temperature, again, we have this one loop thermal correction. And again, what I want to show is we can control the parameter space with analytic study before, and eventually we will find that the analytic study agree very well with the numerical results, although the numerical results is a very complicated calculation. So to do that, we again expand these two thermal functions to the in the high temperature limit. So then we have this leading order terms. So this is the effective potential with the leading order thermal corrections. And phase transition essentially is just to keep track of the evolution of the minimum of the potential. So to find the minimum, we want to solve for this stationary point conditions, where in all three directions we have the first derivative equal to 0. And for simplicity, we will ignore this AS term. So then the S is the S wave will stay at 0 throughout thermal history. And this could give us the right feature because S is suppressed by the kappa S term. So that would make the problem more simple because we are left with only two fields, the Higgs field and this A. And we are going to keep track of the evolution of H and A. So now we expand the experiment condition in the A direction. and found it to be of this cubic equation. And the number of solutions to this equation is determined by the discriminant function. If this is positive, then there's one solution, otherwise there are 3 solutions. And the other direction is the H direction, and we can expand this stationary point condition in the H direction as well. And the number of solutions to this equation is determined by the second derivative. And again, if this is larger than 0, there's only one real solution and H equal to 0, otherwise there are 3 real solutions. So now we start from a very high temperature. We found that because we have this AA term here, which is non-vanishing at finite temperature. So the universe actually starts from a non-zero A. So this is different from most of the single extension standard model, where the universe starts from 0, 0. And it later transfer into 0 something, where something is the wave of the singlet field through a phase transition. And later on, it transferred to the Electroweak vacuum. So this is the so-called 2-step phase transition. But in our case, we have only 1 step because we start from 0 something already. And this thing is introduced by this AA, which is from the dark Yukawa coupling. So this is a special feature of our model. So at very high temperature, if we calculate this discriminant for the for this equation, we would find that there's only 1 solution at high temperature. So as temperature drops, the discriminant becomes 0 at some point. It would become negative below this temperature, and 2 more solutions for the instrument in the A direction would appear as this A1 and A2, and A1 and AS are minimum, and the one in the middle would be a saddle point. But still, at this point, there's the Higgs wave is still 0. And this is actually important because we don't want the universe to smoothly roll over to the electroweak broken direction with a non-zero Higgs wave. We want it to go through a first order phase transition. So at this point, we want to impose the condition that this AS is indeed a minimum in all directions. So we impose the second derivative in the H direction to be positive at this temperature. Later on, as the temperature drops, there's 1 more minimum at non-zero H developed here. And this AS is still a minimum. So we have 2 minimum in this configuration, and there has to be a barrier separating them. So the transition from AS to this minimum, when it becomes lower in temperature, lower in energy, is the first order phase transition that we are interested in. And this is the picture at 0 temperature. So we have, this is our Higgs vacuum. And we still have 2 more minimum in the potential here, but we want them to be of higher energy than the Higgs vacuum, so that the Higgs vacuum is our global minimum today. And this imposes another condition for the parameter space. And also the nucleation condition is harder to derive because it's hard to calculate nucleation rate analytically. So in this paper, these people propose an approximate condition for the nucleation is that the energy difference between the 2 minimum shouldn't be too small compared to the barrier. Otherwise, it would be very hard to tunnel through the barrier. So this puts a quantitative condition for nucleation. So putting all this together, so all these lines are from the analytic study we just went through. And so the shady area is excluded by these analytic conditions. And if the red points, the red solid points are the strong first order phase transition points with nucleation. Others are without nucleation, but with a first order phase transition. So we can find that all the red points are approximately consistent with this white area, which is not excluded by our analytic study. So as we can see from this plot, although the numerical study, which we did with the full one loop potential, it's a very expensive numerical calculation, but it could be very well constrained by the analytic study with just leading order currents in the potential. So, and then I'm going to switch gear a little bit to talk about another aspect of the phase transition. So we know that phase transition is happening, and we found the parameter space where it's strong enough for baryogenesis. And then the question is, how fast do this bubble expand? And this is actually crucial for the precise determination of baryon number generation and also the gravitational wave signals generated from this kind of first order, phase transitions. So the big picture is that for first order phase transition that happens in the vacuum, where there is only the scalar field expanding, the wall velocity will accelerate all the way to the speed of light because there is no friction. The scalar field is not interacting with anything. More realistically, for electroweak phase transition, it happens in the radiation domination era. So it happens in the plasma. So a lot of particles could couple to the bubble wall, and that will introduce friction. So in this case, the wall velocity will not accelerate to 1. And the value of the terminal velocity of the bubble wall depends on the balance of the phase transition strength and the scalar plasma interaction. So now I'm going to talk about how we can calculate the bubble wall velocity in a plasma background. So before that, we have to understand what kind of fluid profiles could form around the bubble. And there are 3 types, depending on the wall velocity. So we have deflagration, which is for the lowest wall velocity, where the bubble wall is moving slow enough so that it can perturb the plasma around it. So this blue shade is to represent the plasma being perturbed by the bubble wall. And inside the bubble, the plasma is static. And another limit is that the bubble wall is moving so fast that it doesn't have time to perturb the plasma in front of it. Instead, there will be a rarefaction wave formed behind the bubble wall. So this is called a detonation. In the middle, we have the hybrid, where we have both the perturbed plasma in front of the bubble wall and the rarefaction wave behind the bubble wall. So an important point here is that the fluid velocity and the temperatures on both sides of the bubble wall are not equal to each other. But they are connected by energy momentum conservation of the whole scalar field and fluid system. So this is the energy momentum conservation equation. And this is also the starting point for our calculation of the bubble wall velocity. So first of all, we want to expand this TAMU nu phi for the scalar field, which is this form, and for the fluid. And we want to take the approximation where the fluid is in local thermal equilibrium. And in this case, its TAMU nu can be written in terms of the thermal quantities as this. And with this expression, one more approximation we can take is that we can work in the wall frame, and if the wall, if we are close enough to the wall, we can ignore the curvature of the wall. So then the wall is vertical, and the only spatial dependence would be in the direction of the bubble expansion. And so we can reduce EMT conservation to two equations. And substituting these expressions into these two equations, we get two matching conditions for the fluid velocity and temperature in front and behind the bubble wall. And also, if we multiply both sides of the EMT conservation by the fluid velocity, we get the following equation. And the first term in the parentheses is just equation of motion of the scalar field. So this must vanish. So then we are left with the second term. And we derive the third matching condition from this, which we call entropy conservation, because this S stands for entropy. And this also demonstrates the equivalence of the scalar field equation of motion with entropy conservation under local thermal equilibrium approximation. And some of you may see this alpha in baryogenesis and especially gravitational wave calculation, because this quantifies the phase transition strength from the energy perspective. So this is basically just the energy release from the phase transition over the enthalpy or the total radiation energy. So this is very useful for calculation of bubble wall velocity and gravitational wave from first order phase transition. And we will use this quantity later as well. So now let me explain how do we calculate wall velocity in each scenario. So for detonation is the easiest one, because in this case, we say the plasma in front of the bubble wall is static. So V plus, so V plus is the fluid velocity in the wall frame. And we say the fluid is static in the rest frame of the cosmic frame. Okay, so in the wall frame, it would be running into the bubble wall. So V plus would be equal to VW, where VW is the wall velocity. And T plus, the temperature outside the bubble, because it's unperturbed, so it would be just equal to the plasma temperature at the nucleation point, which is Tn. So now we have these two known quantities, and we can use two of the matching conditions to solve for the other two, V minus and T minus, which is the quantities inside the bubble. And so now we get all of these four quantities, and we can calculate the change of entropy across the bubble wall. And we can use this we can use this to solve for the real VW. And we know for the real VW, we have to have entropy conservation, so delta S has to vanish. But if we plot delta S as a function of VW for detonation bubbles, we found that it never reached zero. It's always below zero. So, so then we know there's no terminal velocity for detonation. It will keep accelerating. Then for deflagration and hybrid, it's more complicated. Because in this case, we have this shock wave in front of the bubble. So we cannot match anything directly to either VW or except for V minus, because the plasma behind the bubble is static. So V minus would be equal to VW in this case. But temperature, we cannot map either T minus or T plus to Tn. Instead, we should map the temperature outside this whole thing, this shock wave, to Tn. But to connect this TSH plus to T plus, which is right outside this black circle, we have to solve the temperature evolution function across the shock wave. And that requires some numerical work. But anyways, this could be done. And we can map this to Tn, and we map V minus to VW. So again, we can use our matching conditions to solve for V plus and T minus. So so with this known, we can again calculate delta S, and we found that it would cross zero at some point for deflagration and hybrid bubbles. And we identified the first crossing point, the VW at the first crossing point as the terminal velocity. That would that allow us to satisfy all three matching conditions. So this is the system. So this is how we determine VW in LTE approximation. So now we use this method to calculate VW for our dark CPV model for a particular benchmark. And this is a parameter scan. And this the color is shows the VW for the deflagration hybrid points. And we also have a bunch of detonation points, which doesn't have a terminal VW. And we also plot these points in the histogram of alpha n, which was the phase transition strength we introduced earlier. And we found that for this model, the deflagration and hybrid bubbles only occur for very big phase transition with alpha n below 10 to 4 times 10 to minus 3. So this sets a bound for baryogenesis, because baryogenesis could only occur around deflagration and hybrid bubbles in the conventional setup. Another thing we found is that the typical, the wall velocity for deflagration and hybrid bubbles in our model is in the range of 0.5 to 0.7, which is much higher than the value that is commonly assumed in literature, which is 0.1. And the reason why people assume this low value is that baryogenesis is more favorable for lower VW. And the intuition is that the lower the wall move, the longer time you have to generate baryon exclusion. If the wall is moving too fast, it would just take all the baryons into a broken phase, and their spectrum is inactive. So this is the intuition and why people like to choose VW. But unfortunately, this is not the case for our model, and very likely for most of the Electroweak baryogenesis model using single extension. So this has to be taken into account if you're calculating baryon number generation from Electroweak baryogenesis. And we also fit this, we also study the correlations between the parameters alpha n and VW, and also Vn over Tn, which is important for baryogenesis. And we found that, not surprisingly, alpha n and Vn over Tn is positively correlated, and VW as well. And what's interesting is that we found that both of them could be fit by the same functional form of alpha n with different coefficients. So this could be potentially useful for future baryogenesis calculations. So then we put everything together and we calculate baryon number. So as I mentioned before, the real VW that we calculated from first principle falls in the range, which is much higher than the commonly assumed value. In this case, the leading order expansion to VW, which is the conventional method of calculating baryon number, is found to diverge near the terminal VW around 0.6 here. And the other line, this green line here, is the full order of VW, and we found it to behave smoothly towards the terminal VW. And the difference between these two methods is 1 order of magnitude. So this has to be taken into account as well for realistic bubble wall velocity. Leading order calculations will just fail and will give a much larger baryon number than in reality it is. And we also calculated gravitational wave spectrum with the real VW. And we found that to our sadness, the deflagration and hybrid walls are below the sensitivity size of future experiments, while the detonation could barely reach the sensitivity, but that's not interesting for baryogenesis. But fortunately, we have other probes, which I don't have time to get into, for this model, which could also provide a probe of this model. Then I will come to my conclusion. So the CP violation as the baryogenesis model with CP violation in the dark sector can evade the very stringent EDM experiment bound. And the Yukawa coupling introduced a couple turn at finite temperature that would break the Z2 symmetry for the singlet. Therefore, the universe goes through a 1-step phase transition instead of the common 2-step phase transition. And we do numerical calculation, and we found the region giving us strong first order phase transition. We calculate the bubble wall velocity, and we found that to be much higher than the usual assumption. That could modify the eventual baryon number generated. And the gravitational wave, it's unobservable for the deflagration and hybrid bubbles, which are for baryogenesis. And this actually agrees with the common law in the community that electroweak baryogenesis cannot be probed by gravitational wave. But this is model dependent, so I would say this is not the final conclusion. And this is not the only model. So I believe one day maybe we can still find a model, an electroweak baryogenesis model that can be probed by gravitational wave. So that's all. Thank you.
Questions?
Yeah, maybe last slide you show the dark matter detector to test the chi and try the search for ice.
Yes.
Could you say more about this?
Yeah, so this is so the dark matter side is the dark matter candidate is the chi in our model. So actually in our earlier 2 papers, we scan over the parameter space and we find a region that is consistent with baryogenesis and dark matter direct detection. But unfortunately, that was changed after we calculated the bubble wall velocity carefully, because we found that the full calculation using the right wall velocities much lower than what we got in the earlier paper using the leading order calculation. So this reduced the baryon number by a lot. So we have to go to a region that was excluded by dark matter direct detection. But in principle, we can, well, to save that, we have to modify our model by a little bit. But I believe in principle, you can make that still be a valid dark matter candidate and probably in dark matter direct detection. Yeah. And for the collider search, it's the same reason. It's parameter space change. But the idea was that because the scalar couples to the Higgs, so in principle there are a lot of ways to probe that. If the scalar is lighter than the Higgs, then you can probe that with Higgs invisible decay. Otherwise, it could be something else. Yeah. Otherwise, it will not be an on-shell Higgs, but off-shell, and the singlet later decay to leptons and.
While solving the energy conservation equation, do you assume the flat universe?
Yes. So in this case, because we are focusing on the region near the bubble. So I think in that region you can zoom.
Or is it because it's in the early universe where you can use?
Yeah.
So you have quite a few vacuum which are being developed, right? Like a first AS and then A2, AP. So how does the universe move? From AS to those vacuum and then slowly go to the proper Higgs vacuum? So that's the transition detail.
No, it's
The first AS.
yeah, first we have this.
And then you had a couple of more.
Yeah, I have two more, but they all have H equal to 0. So this is something like this in the A direction.
Okay.
But later on, this is a separate minimum.
Okay,
Or,
so this A1, A2 are in the A direction, so they're, but then what's the purpose of this A1 and A2? What's the, why, like what would this A1, A2 do?
Oh, they don't do anything. They are just here because I think mathematical requirement. Yeah. So the actual transition is this AS
S to H. So A1, A2 are kind of dark minima, so the universe doesn't see them.
Yeah, that's right.
So also, does this AS by any chance induce any wave to your Higgs, to this Higgs potential? Like you are putting some wave, giving some wave to the AS, like this scalar field, and then does that induce any wave to the Higgs, to this Higgs potential you have?
Yeah, that's a good point. For our leading order analysis, it doesn't. But in the numerical calculation, you will find a very small non-zero h with this AS. So in reality, it would be a very small h AS. But this is still separate from this vacuum, where we have a much larger h and a much smaller a. Yeah. So in numerical simulation calculation, you will find that there are two very different minima forming, and the numerical would tell you when the equation condition is satisfied and there's a transition.